All right. Thank you very much, guys, for coming to the section, second session of the morning. It's my pleasure to introduce Robert Loew from Stuttgart, and he's going to talk today about something very exotic: ion, Rydberg atom meets an ion, or whatever. It's super cool, okay? So the floor is yours.
It's not so exotic. We did this 10 years ago already.
For me, it's still exotic.
Okay, so this is my outline. I will be a bit faster than the outline, hopefully. And so what we have here in Stuttgart is a so-called ion microscope. So it's a new way to image ultra-cold matter. And I want to perhaps introduce a little bit to this ion microscope thingy, which is a very German thing. So you see, this is Germany. And the ion microscopes, pretty much the first version was in Josef Vortag's group in Tübingen, where they built a thing where they can put ultra-cold atoms into ionic state, put it through some ion optics on a spatial resolving detector. And then there's the version we have here in Stuttgart. This is the one which I want to talk a little bit more about. And there's another version in Kaiserslautern. All three original ion microscopes are in the southwest of Germany. And there's a new one now in Hamburg from the group of Klaus Senkstock, where he has an ion microscope where he had like two ion, electron and an ion microscope. So the Hamburg people are richer than we are, so they can afford two of these in one machine. And what you can do with this, so we will do here some spatial imaging of correlated states, in our case, a molecule, ultra-long range Rydberg molecules. In Tübingen, Josef was looking at also a correlated state. So this is like anti-blockade or blockaded physics, which you can do as also a spatial resolved imaging technique. Herwig Ott in Kaiserslautern is more doing like momentum imaging, and he has still a heart for this trilobite molecules, and he has done a lot of studies during the last years there. And Klaus Senkstock is going to study some crazy plasma dynamics in this machine with, I think, krypton gases right now. And he will also change to some of the first row elements. I forgot which one. Okay, so what's the concept of an ion microscope? So we have like the two types which are typically out there. So the upper one is like from our group, which is made for spatial imaging. The nice thing is like from the length we have, it's like 1.5 meters, we can go to something below 200 nanometers. So if you make this thing 10 times longer, you will end up at about 20 nanometer resolution, which should be doable with the technique we have nowadays. And the thing in Herwig's group is like more like a drift tube. It's like for momentum space imaging, which can basically go down to recoil resolution of momenta. So what we have is down here a science chamber where you produce some ultra-cold matter, and then you transfer this by some means into ionic states. And here the science region is here. And then on the other end, you have a spatial resolving detector that's typically a multi-channel plate with some kind of electronics behind that you really can see where this ion has hit the detector. And then you can do this spatial imaging, or you can do like this momentum imaging, like in Herwig's group, where you have like energy resolved spectra of different Rydberg manifolds. And in our case, we have this spatial imaging. Okay, so how is it built? How is it set up? So basically down here, we have here Siemens lower laser cooling of rubidium. Then we have a transport beam to bring it into a science chamber. In the science chamber, we have a very well shielded area with all kind of field plates to really have as good as low stray electric field that it can work with free floating ions. So we have no ion traps. So the atoms, we make an ion and it's just hanging there for a short time until the leftover E field drags it away. And then we have a detector up here and two more ion lenses, which are basically 3 cylinders stacked on top of each other. And then we guide it into the detector. So how does it work? So basically, this is a very schematic view. So we have exactly how it works, yeah. So we just apply on the order of like 2 kilovolts difference on this different stacks of cylinders and guide the atoms there. And with this, we can magnify by just changing voltage up to 1,500. We get well below 200 nanometer resolution. And the nice thing is the field of view is quite large, like on the order of 30 microns, and the depth of field, it's just the time of flight of the ions, we have something like on the order of 70 micrometer. So this means we have a huge volume we can image with on the order of a few hundred nanometer resolution. And we have made a little experiment. We have a little diffraction pattern of an ionizing beam. So we bring a whole cloud of atoms into this region. We have a beam of laser light which just ionizes the stuff. And then you can basically get the full 3D reconstructed picture of this atomic cloud in this science chamber. Okay. So what did we do with this? Now, as it's an ion microscope, let's do something with an ion. So we have studied the interaction of an ion with a Rydberg atom. And how does this work? So we take an ion, and we take a Rydberg atom, we apply electric field, and then you get the well-known Stark map for rubidium with the manifolds and the outlying low L states due to the quantum defects. And if we now produce the electric field, not by external field plate, but by an ion, and we place a Rydberg atom close by, then we of course have diverging field lines. So this basically deforms our Stark map a little bit. And it looks something like this, that we have the ion sitting here, and then we have this different state. And the states we can look at is like the S and the P and the D states. These are states we can appraise easily with our lasers. And what's interesting is, of course, what happens if we come to this interaction regions where this low L states move into this high L manifold. So as I said here, so the two things we want to look at is like this NS state, which is coming from below into the manifold, and the NP state, which is coming from above into this manifold. Let's start with the upper one, with the NP state. As you can see, there's a minimum, and we can trap something. And just to show you that the chameleon is our motto of our experiment. And if you cannot remember ion microscope, if you see a talk somewhere and there's a chameleon, you remember these are the Stuttgart people with this Rydberg ion stuff. And the other one, which is not trapped, which is surfing down here on this NS state, down this manifold. These are the two scenarios they have: trapped Rydbergs and surfing Rydbergs. So let's start with the S state, with the surfing Rydbergs. So the S state with the ion, so this is down here. And if you zoom in, then you see that we have basically here avoided crossings going through this S state going through this manifold. And if you imagine what could happen there in this avoided crossing, if the atom is coming from the right and following this potential curve, there is an avoided crossing, and you have some kind of Nanocina probability to either go down or just to rush through this avoided crossing. So if the thing is fast, it goes through. And if this atom is slow, it will just follow this steep curve, which indicates already something interesting. So if this particle coming in has a high speed, it will stay on this very shallow slope, and it will take a long time to reach actually the nucleus, while a slow atom will follow adiabatically this curve and will rush down much, much faster. So in a kind of a chemical reaction language, it's kind of in reverse, that the fast particles react slower and the slow particles react faster. That's the story we want to sell here. So how do we do this experiment? So first, we have a laser system to make a 2-photon direct ionization of a rubidium atom. Then we have a second laser system to place a Rydberg atom at a certain distance. And then we let the system evolve, like let them collide or whatever we want to do with this thing. And then afterwards, we want to detect the ion and the Rydberg spatial resolved. So we give the ion a little pre-kick to let it fly to the detector, and then the Rydberg atom is afterwards ionized and also kicked towards the detector. And then on the detector, we have one click and another click, and then we can look at the correlation. If the one ion was here and the Rydberg now ion was here, then we can learn something about the dynamics of the system if we do this time resolved. So the first thing is, like, we do now no time evolution. We just want to see how we can place the atoms in a certain distance. So what we do is, like, so you have this C4 polarizability potential of this Rydberg ion pair state. And then what we do is we just make this ion. And now we change the detuning of the Rydberg laser and follow this line. And by this, we can follow the distance between the two particles. So if we are up here, we will excite a Rydberg here. And if we're down here, we will excite a Rydberg in this region. So by this we can dial in the distance between the two particles to start with. So this is a potential curve, and this is the overlap to the S state. This is the state we can access. And then if you do now this excitation and you look at the detector, so what we do is like we place the ion at the center of our image, and then we just check where did the Rydberg atom arrive. And if you have a small detuning, then you see we are kind of further out of the C4 potential. And if we change the tuning, we go down, 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 become closer, closer in. And you see how this Rydberg atoms, which are out here, come closer and closer to the core. And by this, if we plot this, then you can directly map out this C4 potential in real space with this ion microscope. And the length scale is typically on the order of a few microns. So we typically use Rydberg states on the order of like 40 to, let's say, 140. So that's the ballpark where we are. Now what you can do is like, now we can let the Rydberg atom start here. So we basically excite the Rydberg atom at this distance and let the thing go. And then we want to see how this collision process works. And then what we do is we just look at the center of mass as a function of distance with respect to the ion. And you see that the whole distribution more or less stays localized here on this 30 micron distance. And if you look at the time evolution, so I have two snapshots here, then you see that 0 microseconds and 80 microseconds, some of the atoms have dared to come in, but it's rather a slow evolution into system because its potential is still very shallow. If we do it on the other hand, inside here, where we have like the steeper potential, and we have also excited the ultra cold atoms right at this spot. So this one is slower. So this atom has a nice probability to fall down this Landau-Sina crossings. And if you do this, then you see immediately, if you have the center of mass evolution, that this is more curved down. It's a little bit noisy, the data, but still from the picture, you can see how now this collision dynamics has a much more rapid evolution into this high L states, and it's really raining down here towards the core. So if you want to have this as a movie, so we have here the -3 megahertz. So these are the far apart particles outside of the manifold and rushing with high speed through these avoided crossings, avoiding going down directly. And these are the guys which are more inside and go down faster.
So, sorry, you said this is an S Rydberg state?
The S state, yes.
Why aren't these spherically symmetric?
Okay, that's a good point. This is the question of the polarization. We have two photon excitation, and by the selection rule of the polarizabilities, we have these positions out there. And also the second thing is like we have an elongated laser beam. So the radius would be something like this, but we cut out basically this direction. So there's two things. And this is just a summary of this paper, which was just published last year, where we have simulated this dynamics with the help of Peter Schmelker's group. I mean, it took us 1 year to do all this simulation to be really sure that we see the dynamics we see, because it's quite complicated dynamics, because we have to do full 3D calculations with all these Landau-Sina crossings, and it was numerically quite heavy. So you can read this paper. If you want to read the appendix, you should be fast awake because it's quite heavy. I think the referees did not really read it, so but they liked it. So, okay. Yes.
If you go back a few slides to where you mapped out the polarization potential.
Second, this one.
Maybe before.
Yeah, it's low.
Yeah. Right. So, I mean, from the experiment, the farther you come in, the larger the avoided crossings become, right? The further you come in, right?
Yeah.
So does this mean that your uncertainty mapping the 1/r to the fourth should become larger, right? Or no?
No, because this is a static picture. What we do here is like we just change the tuning and excite exactly at a certain distance. So this, what you see here, is only the overlap of to the S state, to the dipole transition. So we do the snapshot and directly image where did we excite the Rydberg atom. There's no dynamics at all here.
So this is I mean, these blue things, blue squares or things.
Yeah, so it's getting more faint down here, yes?
It's becoming
more faint down here because
I
we have
see.
less S contribution.
Okay. So
But still, between the two crossing, it's quite S-ish still.
now explain. It's the color.
Okay. So this was just a warm up. Now let's come to the history of the Rydberg molecules. So this is actually what we did beforehand of this study. So we want to bind these two guys together. So we don't want to have a free collision dynamics, or we want a bound state. And I thought, like, since I'm here, because the whole Rydberg stuff started here. So what is a Rydberg molecule? So one is an excited state. It's ultra long, so you have to put it far away. And it's not actually necessary that these two guys touch each other. They can basically also be so separate that there's no mutual overlap of any wave function. But of course, the first one were the ultra long range molecules by Prismin and Hossein invented here. Then later on, we had these macrodimers, which were like the bound state of two Rydberg states. And the thing I want to show you today is the bound state between an atom and the ion, which we call the flipping dipole bond, which is a kind of funny binding mechanism. But let's just go through the history. So in 2000, there was this famous paper here, which we had always on our desk and said, like, we do it at some point, but we had no time. And then there was another paper where really these butterfly molecules and all these exotic animals, trilobites and so on, came more to life. And then in 2009, we just did this experiment by just saying, like, let's tune the laser to the left and see what happens. And what happened was exactly that we found this kind of molecules. It was actually quite easy. We could have done this already 9 years earlier, not 9 years, 7 years earlier. But from this, it started that people started to do all kind of this exotic molecules, like this one here, which was done in cesium. In cesium, you're closer to this manifold, high L manifold, so you get easier mixture of this high L states, and the stuff looks even more exotic. And then Rydberg and so on really harvested all the different species you can find of these Rydberg molecules. But then there was also this paper here that you can make this bound state of two Rydberg atoms. And the first observation was then done by Jim Shaffer, still in Oklahoma at this time, where we had this macrodimers. These are huge objects, like of almost 10 micrometer distance. And then in 2021, there was a new type of molecule, this iron Rydberg molecule, which basically was also a calculation from Johannes. And this is the thing we then were able to realize in our machine. So how does this work? So we have the same setup as before. So we have the iron, the Rydberg, and now we are living in this curve here. And then you see there's a little bathtub. And we hope that we can find bound states in here. And if you do the calculation correct, then you see that these are actually avoided cross, or that this basically is not rushing through. So it's not a real crossing, avoided crossing. And then you have this little quasi harmonic potentials, and then you can find bound states here. And the nice thing is that these bound states have a distance of a few megahertz. So something which we nicely can resolve with our detectors. And the distances, as you see here, is on the order of like 2 microns. So this is something which is also quite suitable for our ion microscope. So how does this binding mechanism work? So this is really peculiar. So what we have is on the one side, if we are close to this ion here, then we have here a high L Rydberg state. So this means that we have quite a localized wave function, which means that we have the ionic core of the Rydberg sitting to the left. So it's repulsive here, and the electron is hiding behind the ion. So this is a repulsive state. Then on the other side, we have this kind of p state character, so a low L orbital coming in, and then we have a more accumulation of the electron on this side. So this means it's an attractive branch. So this means if this Rydberg atom is moving from here to here, the electron has to jump back and forth from the front to the back to make this attractive and repulsive branch. Okay, so these are the two type of bonds. So we do the same thing. We just make an ion first, then we do a Rydberg excitation by just tuning the laser exactly to this position that we hit one of these bound states. So by this we do a photo association of this of these molecules, and then we do the same thing. We first kick the electrode, the ion a bit, ionize the Rydberg atom, and put them both on the detector. the first thing we do is like just a pure spectroscopy. We just count how many ions we get by just changing the tuning. And you can nicely see that we find this lower lying states here, and we find this nice series of vibrational states up here. And you could even see a little bit of this parity oscillation, that even states have a little bit higher amplitude than the odd vibrational states. And we have a resolution of on the order of megahertz, and then you can just follow this for many, many vibrational states. And okay. And now we want to do, we want to see that we really have a bound state. So what we do is we produce ion here, and then we apply, then we either drag the ion alone away, or we produce the molecule and apply electric field and drag the bound state away. So the molecule is twice as heavy as the ion. So this means with this extraction field, if there is no Rydberg atom attached, the ion makes it all the way to the upper right corner. But if we hook up a Rydberg atom on it and it's a bound state, then it only makes half the way, which proves that it's really a bound state of an object where we drag on the ion and the Rydberg is just attached to it and it's a real molecule. Okay, and now the best thing, of course, of our ion microscope is that we can do spatial imaging. So what you see here is we have, now went to the 69p state, it's a little bit higher. By this we have a size of the Rydberg molecule, which is like 4 microns. And depending on the polarization, you see different patterns. But again, we have like first the ion we put in the center, and then we just check where does the Rydberg atom arrive, and then you can directly see the size or this Rydberg molecule in real space by this imaging technique. And this is, of course, an average of many, many, many pictures. And then we find the probability where to excite the Rydberg atom. And it heavily depends on the polarizations we have there. Okay. Now, if we have a Rydberg molecule, the one thing I wanted to do since a long time, I wanted to see a vibrating molecule. And the nice thing is, like with normal molecules, it's a little bit hard because, like, if you take a normal ground state molecules, H2 or NO, then you have typically vibrational frequencies in the terahertz or above terahertz regime. On the other hand, also rotations are very, very high, and it's really hard to see this in real time. But if you now plug in a molecule with like 4 micron distance or size, then you see that the vibrations go down to the megahertz regime. So that's something which you can nicely resolve with our detector. On the other hand, the rotation here is still on the 100 millisecond regime, which is still too long. It's much longer than the lifetime of this Rydberg molecule. So it means you can watch it vibrate, but watching it rotate is probably a different story. So how did we do this? Like again, we do this excitation for the ion, and then we attach the Rydberg atom at distance. The only difference that we apply a small electric field, and this electric field distorts a little bit the position where we have where the Rydberg atom is photo associated. So without electric field, we have these black curves, and if you apply an external electric field, then you see that we get a displacement in this bond length, or we get a stretch in the bond. And then if we switch off the electric field suddenly, and we have produced this atom, let's say this position, electric field off is again this curve. So the wave packet is projected up here, and then it can start to oscillate back and forth in this potential. And this is exactly what we do. So we have now a wait time in between. So we let the things slosh around. And then we did a lot of kind of simulations. And the thing is, like, the amplitude is still quite small. It's like only on the order of like 30 nanometers. It's a very confined object, although the whole thing is like 4 micron in diameter. The amplitude of the oscillation is only like a few 10 nanometer. But we were a little bit lucky, because what happens in our extraction pulses is that we have an electric field present, and we do a little bit of a momentum imaging on a spatial imaging. So we have a little bit of momentum, and the atom is going through the center, then it has momentum, and then it flies in this direction, and it comes back and flies in the other direction. By this, we magnify these oscillations a little bit, and we can really see now on our detector, this is the position of the Rydberg atom, you can really see how this thing starts to oscillate. And if we extract the data, then you can see a nice oscillation and the frequency matches exactly to what we have calculated. This is so we can really look into coherent dynamics in this system. And we have done all kinds of simulations. We have done 3D classical Monte Carlo simulation. We have a 1D quantum mechanical model. And the damping here is mostly due to lifetime issues. So in principle, this molecule should be live 10 times longer at least, but it doesn't want to. We don't know yet why, but probably it's some technical issue. But in principle, one should see this for many, many oscillations. It's an anharmonic oscillator. One should see some revivals and fun stuff like this, but our molecule said so far no. And this is a movie really presenting in real scale how this molecule looks like. So up here is the ion, down here is this Rydberg atom, and you see how this oscillates on a really small amplitude. And the crazy thing, I mean, it's not touching at all. It's just the effect of the Stark effect produced by the ion that we can have this bound state. So in principle, if you have just a gradient of electric field, you should also be able to just keep the Rydberg atom at a certain position in space. And now you see nicely how this electron hops from one side to the other side. And this is why we call it as this flipping dipole bonding mechanism. It's not the simplest word yet. Okay, and now I will come to my outlook. I mean, I hope that we have some trimer signal, but we have no trimer signal yet. Now the idea would be the following. So we take one Rydberg atom, one ion, and we attach a Rydberg atom and another Rydberg atom. In principle, this should be possible. And here's a little overview of trimers, because this is a trimer workshop here. So, I mean, we have done some trimers for this classical Rydberg macrodimers, where we have attached more and more ground state atoms. We were able to go to dimers, trimers, tetramers, pentamers, and so on, to like almost putting a whole BEC into it. I don't know how to call this, a millionmer. And another nice realization of trimers were done in Manuel Bloch's group in Munich, where they have these atoms and lattices and have seen this kind of trimer resonances and kind of chain reactions, how this excitation goes through the system. Has done this one here. So I only have like rubidium, so it's not my job. Someone else has to do this. But we work with nitric oxide and also a Rydberg state of nitric oxide. And this is also like a heteronuclear molecule living perhaps in the vicinity of a Rydberg state. But this is a hot vapor experiment, so it's a little bit more tricky to see something there. And there's these two works from Daniel Bosworth in Peter Schmelker's group, where they have done a hybrid of our Rydberg ion molecule with the old macrodimers. So putting an ion Rydberg atom and a ground state atom close by. And this one here, I think this is a little bit brave for the experiment to have an ion Rydberg ion trimer. I mean, you have to make two ions, and then you have to be quick enough before these two guys take off to get the Rydberg as a glue in between. So we did it, said like we do it a different way. We take an ion and we glue one Rydberg atom here, and we put another Rydberg atom here. And we have done now some, I would not call it calculations, we are experimental physicists, so we try to figure out how this interaction potentials would look like for this system. So what we did is the following. So, I mean, this is the geometry we have. I mean, for us, too many numbers for experimentalists, but you have to really take into account the whole orientation, the induced dipole moments of the Rydberg atom sitting in the ionic potential, the direction of these dipoles, and the van der Waals interaction between these guys. So what you have, like for the S state, I mean, we have the ion Rydberg C4 potential. This is stuff which just goes down. This is a quite simple potential. It's an unbound system, so it's just spherical and round. And then we have the van der Waals potential, which is repulsive. So this is also kind of harmless. And then you have to add the dipole-dipole interaction, where we just took the dipoles which are induced by this ionic field. And then if you move, so what we do is like we fix the ion here, we put one Rydberg atom here at a certain distance, and then we just take the second Rydberg atom around and we just calculate the dipole-dipole interaction due to the induced dipoles we have. And for the S state, I mean, this is kind of harmless, but you see them some nice field lines where you might think about you could produce some bound states here. I mean, this is something we can discuss later with many beers, I hope. And for the P state, if we want to have really trapped ones, and we just take, this is our Rydberg ion potential. So we have the ion and we have the Rydberg atom bound here on this rim here. Then we have to add also the van der Waals interaction, which is like our PP interaction. So we have this fourfold symmetry here. And the ion, the dipole part, of course, looks now also quite complicated when we move around here with this ion in this landscape. And you see there's a quite rich landscape. And this is just putting this, we take just these three things and add them up, which is the most illegal way to do it because it's not even perturbation theory, it's like zeroth order. But then we get something, potential curves, if we put them all together, so this is all, as a function of the angle. So we have this linear molecule. Now we are interested if we can get something, not in the vibrational degree of freedom, but in the azimuthal degree of freedom. And if you look into this little wells here, there seem to be also like megahertz-based bound states, but these are now rotational or kind of rotational states, which might be interesting to look at because before we had no access due to this slow rotational dynamics that we could see something like this. And this is something we would like to investigate more. We have now started to calculate the linear case. This is something we were able, but if you start to angle the whole thing, the calculations are getting quite heavy. And but for small angles, I think you can do some perturbative approaches. Okay, so with this, I'm at the end. So we have this ion microscope. You can choose where you start, like above the manifold or below the manifold. You can have like some rich collisional dynamics, or if you start above, you can have these bound states. And now the future is that we want to go from 2 particles to 3 particles, which is a technical challenge for our detector and everything. But this is where we're heading right now, and we have started to do calculations, and probably we would need some help because it's too much. Okay, and this is a group, so it's everything in Tillmann's Fau group. Basically, everybody has left now, so we have only Jenny is left. She's the only PhD student. A new PhD student will join. And of course, we are looking for people to join our team, PhD or postdoc, or super postdoc, whoever wants to join should talk to us. And with this, I have a chameleon question mark about what I have just showed you. Thank you.
Thank you, Robert. Thanks for questions, please. It was so clear, no one had a question. Okay, Leah.
You alluded to some detector problems with the 3 particles. Can you elaborate on that a little bit more?
So the detector is basically made for detecting 1 particle, and then there's a meandering wire structure. So there's a cloud of electrons coming, and then there's a wire, and then the 2 wave packets coming, that makes click click, and then you can calculate where it was. So if you have like 2 particles at the same time, it's get a little bit convoluted. But you do this delaying technique. But if you have 2 identical Rydberg atoms, then they arrive at the same time, and we need to a little bit more of understanding how we can delay it a little bit or to disensemble this many clicks we have there. But I mean, the idea would be to use 2 different Rydberg states. So this is, and then using some field ramps to ionize the one first and the other one. And yeah, but it's getting involved. Like even the 2 particle correlations we have, I mean, you have to see we have like 10% of the cases 2 particle correlations. Now, if we continue with the same kind of Poisson distribution, we have 1% in all the other ones. So it's, it needs more tidiness.
Please.
Yeah, beautiful talk. But I was wondering if you think you understand the associative ionization process. I know we collaborated on this years ago and published a paper on it, but I really felt it wasn't I really didn't feel it was totally understood at that time.
No, it's not. I mean, what we have, I mean, for the collisional state, we just see that it comes in and there's a little burp coming out afterwards, but this burp, we couldn't extract any information. So we would need a little bit more better controlled, also like in the azimuthal direction to see where it comes in, where it comes out. I mean, with momentum conservation, you can basically choose, or you can deduct this, but the data was not good enough. And we didn't continue on this conditional dynamics because it just goes down somewhere. And the magic 4 wave numbers, it goes down and comes out again. We have not looked into this again because, I mean, we need a little bit more control to do these experiments. But this spaghetti, I mean, it just dismembers your in-particle wave function.
It seemed like it was being triggered by the butterfly potential, as I recall.
In this old case, but here we really directly go down with this avoided crossing, with this Landrosina crossing. We just go down into this low seeking states, and I don't know what it does down there. And of course, it's interesting to study, but I think we need a little bit better control over the energy distribution to start with. We have like still microbar Kelvin clouds, so if you have to be a little bit colder, then you can choose a little bit better the energy to start with, and then you could. I mean, we have a lot of simulations of things we wanted to see, but we were not able yet.
You.
Really good stuff. I'm trying to understand the kind of vibrational states you're using to observe this coherent vibrational dynamics in the between Rydberg and the ion. So, kind of going back to your
Make the move you are.
could you go back to where you had the energy levels for the vibrational states?
Okay, sorry. Okay.
Yeah, so here.
Let's have
Yeah.
one here, yeah.
So are you in one of these like vibrational eigenstates, or are you in some superposition of?
No, we can, I mean, as you've seen from the spectrum, we can go to the eigenstate, so we can go to the lowest vibrational state. So this basically this is a curve for no electric field. So this is a curve for the electric field, and it makes kind of sense that it's different from the one side to the other side because you have the ion and you shine electric field from this direction. So it places both in the same way. And then we can excite here in the ground state, and then we quench off the electric field, and this wave packet gets basically projected up here. And then it's a superposition of, let's say, ideally of, let's say, 3, 4, 5 states. And then this thing is starting to sloshing.
Gotcha.
And of course, you can do different ways there's different ways that you can try to re-excite exactly one wave packet up here by doing some microwave transitions and stuff like this. But we were lazy, we just snapped it with the E field.
I see.
But if you put a microwave field in there, then you can just exactly go to a certain specific eigenstate up there.
Okay, thank you.
Which is the eigenstate, which is not so interesting because it doesn't move.
Right, exactly. No, was
Benching is
my
the
question.
trick.
Yeah.
Yeah, so for the long range dispersion coefficient of this Rydberg ion Rydberg system, I have tried to calculate the dynamic polarizability of these Rydbergs.
I mean, we just take the C4 potential. We just have an electric field, yes, and then we just take and then we calculate. So it's a little bit more interesting because I mean, if you have a normal Stark effect, then you have just one electric field, the component. But if you're in these fields, you have to take the gradients at the higher order. So we go all the way to the 6th order to calculate all the higher moment, because over the Rydberg atom, you have a change of the electric field from the beginning, or from the one side to the other side. So you have to take, so we found out if you go to the 6th order, nothing happens anymore. So we take really the higher order effects in, which means like you have to all the coupling to all of the delta m's to the 6th order, they count. But we have a good code by now which can do it actually quite fast. So we have theory group, Hans-Peter Büchler's people, and the code is super efficient. And it sounds more horrible than it is. The most horrible thing is this one here, when you start to tilt one of these guys, then it's over.
Because it's like a highly anisotropic, right?
No, because then you project all the L states. You have like, let's say, a stretch state, and everything is good. But if you start to rotate it, you have to rotate the spinor, and then immediately all the other guys pop up. I mean, if you have a stretch state, then you have like one population here. But if you start the thing to rotate, then all the L states, all the N stuff. Okay. And then the computer explodes.
But not if it's a quantum computer, right? Any more questions? Right, so let's thank Robert again.